pain. And she's always going to tell us. Okay. You guys can hear me okay?
Yep.
Okay. So this is episode number 4. And see what we got going on. Now, leftovers from last episode, I left you pretty quick with the standard model. Now, you could go through your entire life not knowing the standard model and be just fine. In fact, you can learn mechanics and you could learn electromagnetics. You could do two whole classes in physics and not know a thing about the standard model and be just fine. But I find it interesting, and since Dr. Strauss is a big part of my class, I felt like I needed to at least tribute a little bit to him and talk about standard models some. Since this is a physics variety show, we definitely do a big variety of topics. And if you're expecting chronological, this leads to this, that leads to this, that's sort of there with the foundational stuff. Like we'll talk pulleys today, but I also want to take those broad jumps and talk about some of the other stuff in physics because it's summer, we're having fun. There's no test. I thought about giving a test or something, which would be a pain in the butt to make up, but more like, okay, so you guys can tell me what you think, but since this is a testing course, just a experiment. But I'm looking at the fall. I'm going to do 2 classes in the fall each week, and I'm only going to charge $5 a class. And each class is an hour and a half, but you got to sign on for the long term. And this is starts with physics 101. Okay, so like walking and running and all that kind of stuff, like we did out in the West Lawn. Somehow I got to put that into a show. And so we'll talk about it but then there's got to be some kind of even though it's not really for high school credit, but there's going to be some kind of way to evaluate. So I thought, well, I could experiment with you guys and give you a test at the end. It also helped me to know if anything got through. It could be open note test, whatever. And then if you do well, you would get some kind of special certificate. Everybody gets a completion certificate, okay? But this is like, hey, did outstanding, but then that made me think, well, okay, but this is summertime and we're supposed to just be relaxing and not stressing about a test. See what I'm saying? Even though it's not for credit. I know what you guys are. I got to be the number one. And I don't want to bring out that competitiveness with you. So I go back and forth whether I should somehow put some kind of evaluation on this or not. Either way, it wouldn't have mattered, except the only person that would see it would be me and you. No one else would even see it. Unless you show up as the top. See what I'm saying? There we go. So saying all that, I encourage you all to direct message me or to comment me your ideas, because that's part of this is a two-way street here. I'm going to teach you what I know about some physics, and then you're going to help me let me know whether it's being effective or not. Okay. So the quarks and the leptons here are the fermions, and I'm going to show you the reason I'm showing you this. I'm going to show you the source that I started going to. This is a really good source here. This Quantum Diaries, and it's a blog. There's like the standard model of beautiful but flawed theory is where I got the image. Then I went back and searched the story, and it's a really good. It's well written, but it talks about these problems with the standard model. And kind of a little bit more about how it works. And so if you're interested, realize this is what's called high energy physics. And if you want to ever work with Dr. Strauss, this is what he does. This is his job. So this is a brand of physics. It's not really theoretical with the Large Hadron Collider. It's empirical now. Empirical meaning there's a lab associated with it. For a long time, this was just theoretical until we started getting particle colliders and linear colliders, those kind of things. So anyway, now it's more empirical physics. It can be, but and that's what Lloyd, I'll talk about the field trip here in a second, but that's what Dr. Baum talked to me about. He said, is it okay if we talk to these when we're going to come next week to the Actually, a week from today is the field trip to OU. But he said, is it okay if we give them some theory? I said, yeah, I mean, let's do both. Don't just show us labs. I mean, talk to us about the theoretical side of physics. So we're going to see that as well. And I'll talk about that more in a second. Okay, so I wanted to show that. And then I wanted to show this source. It's a slideshow. It's 83 slides. It's from a professor. I'll tell you the truth, I didn't even bother getting the name. I just started looking through the slides. And there's a bunch of them I could show you on the internet, but it's something else we're talking about tonight. But I will put this link to these 83 slides. And it's well done. It's not all, at least the ones I've looked at so far. Like it's written for more of an introductory quantum course, not for the hard-nosed Calc 3 types. Okay, as far as I've seen so far. Anyway, I'll put this in the screenshots, and also I'll put the link in the comments to this 83 slideshow. It goes into more detail if you want more detail on the standard model. It might be something you study this for one day this summer, and then kind of put that away in your brain bank, knowing that then when Higgs comes up or something, you'll have at least something to latch on to. Okay, so now we're ready to actually start this episode. And so I'll talk about field trip updates here in a second. Then we'll have to put it on pause for a second while I show you the scene from Interstellar, which were about tides, trying to dramatically make my point. Then we'll talk about tidal forces and the days on the Earth getting longer. And then we'll get into the kind of the meat. And what happens is I spend so much time on the fluff here that the meat finally comes up and we are almost out of time. But this time I'll try and do a better job of getting to the Pulleys 101, talking about the forces involved. And there's like 5 rules to Pulleyland. We'll learn those, and then we'll kind of see how to work pulleys and show how that leads us to machines, input, output force, efficiencies, all those terminologies you use, of course, work. But all that terminology you use in machines and energy. So I'm going to kind of use pulleys to get my foot in the door on machines, because a pulley is a machine, but it's not all the moving parts and gears and motors, and that's just another example in physics, theoretical physics, of a machine. Lots of simple levers. Okay, so that's what we'll talk about. I'm trying to talk about. We don't get to, we'll work on next time. Okay, first, field trip update. So the physics buildings, I wanted to do those first, and that'll be a week from today. That means that on the 17th, 6/17, there you go, 6/17, we won't have one of these. Okay, we won't have a Zoom that day. Now, he said it has to be in the afternoon. He's still trying to work out the logistics because he's having to coordinate with like 4 or 5 different people. So, and they're going to do like 15 minutes this person, 15 minutes this person. The whole thing shouldn't last more than an hour, maybe a little over an hour. I mean, hour and a half, probably at the most. Depends how long-winded they are, but I'll let them know that you guys got to be somewhere. And we'll be looking at both physics buildings. I'll film it. So if you got to work a week from today, I'm not the best I'll have a selfie, and I'll try and be cognizant that I'm not, taking film on my feet. But I told them that we would have like 8. I said probably 8 to 10, probably no more than 10 live people there. So me plus up to 9 of you. Well, there's only 10 of you. So I know some of you, these are my members here. But it doesn't mean, like, if there's only 2 of you coming, doesn't mean you can't bring your brother or your dad or your mom. I think we just can't, we're supposed to have no more than 9, let's say 8 with me people. Maybe 9 with me. Okay. Sorry, I'm not opening up. I see there's a chat. Hold on a second. Jacob is my chatter. He says, my computer is saying it needs to update in 10 minutes. Oh, okay. I got you. I hear that myself. I think you can, Jacob, you can, say no or do it later, I think, at least on Macs. Just say you'll do it tonight. just as it turns it off, turns that part off. All right. And then the Stevenson Research Center, he came back to me and said, look, I'll do it here. I gave him the dates. He said, any of those dates, we'll figure out a way to do it. So let's first get the physics building tour out of the way. And then the next week, which would be like probably the 22nd or 24th, somewhere in there. Really? All right. Fair enough. That's weird. Okay. So we'll do the Stevenson tour then, and that's going to be good. He's the head of the whole department. At least he was. They change heads all the time at college. Anyway, he was last time we toured a couple of years ago, and he was excellent, really good. He's an authority. He knows all this. He knows what all these labs do. He gives you all these details. He's really good. That was fantastic. So that's also coming up. And on that day, we won't have one of these sessions. Okay. Questions on the trips, field trips coming up. I will put a survey in the Facebook group to kind of see, get an idea. And I may end up sending emails to everybody because I really want to know. I don't want to show up with just me and one other dude, you know. I mean, if people can't make it, then I'm gonna have to call them off, which they're gonna get pissed at me because they spend a lot of time putting it together. But I don't know if they're satisfied with me holding a camera. So they probably want, at least 4, 5, 6 of you would be great, but 10's the limit. Okay. Now I want to finish up some stuff on tides. So remember, just as a review or wrap up from last time, it came down to this, that tides on Earth are caused by the moon's, mostly by the moon pulling on the water like it pulls on the land, but it pulls on the water. Water's lighter, but it's closer. So there's a tide. There's like it's called a high tide, and then there's a low high tide on the other part of the day. And we talked about that so it comes around twice. Tides do every day of the year. And so this was the reason why you have a high tide on the side close to the moon. That's because you're closer in that inverse square law. You're closer, so the water is pulled up more. And then the reason why the other side is still a high tide is because that water's left behind because the Earth itself is 5 times more dense and gets pulled towards the moon. Okay, and then that explains, hold on. That explains this, because this shows the tides every day. Well, look, this is one day here. So this is the high tide, then the low tide in between, and then this is the high tide. Here's the high tide. Here's the low high tide. So you'll see that kind of pattern continue. Okay. So now I want to stop the thing here. And for those watching, let me stop share. Okay. For those watching this video, just make sure that you go, at this point, you hit pause and you go down and maybe open up 2 tabs, but you go down and then watch this Interstellar. I know you've probably seen it, but it helps make my point. So we'll watch a little bit of it. All right, let me share another screen then. Right there, I think. Yeah. Okay, let me share that. Sharing that. Okay. So first off, that's that I was talking about. If this comes up. Okay. So he does a good job. Like I say, these slides, this is the show I was talking about that you ought to watch sometime this week on the standard model. And I'll put that link in there as well. But it goes through a little history of it, which of course I love. And then it goes into some more of this, when those particles were discovered, when was charm discovered, when was the bottom quark discovered. This quark idea, he just died. Murray Gell-Mann, who came up with the quark idea in the 1960s, he died not too long ago. He lived in New Mexico. I've always wanted to go to his place. He lives up there kind of by Santa Fe, I believe. Anyway, so this gets into all that, leptons, quarks. And so I'm not going to show you the whole thing, but that's what I was talking about. Okay, now let's go to the interstellar. I'm going to set the mic here. And then let's probably have to watch a commercial or something. It's been too long. But let's watch this for a second. And imagine you've seen it. But if you haven't seen it, we're deep into the movie now. And they're on this other planet. It's a larger planet, a little bit slightly more massive than the Earth. And it's much closer to their star. That's how I remember it. And maybe the star is just bigger. But I think it's much closer to its sun. And so the tidal effects, we don't get a whole lot of tide from our sun because it's so far away. But I think it's the sun that they're orbiting that's causing it, or there's a moon that's close by. I got to go back and watch this movie again. But the point is that another massive body is causing these tides.
Go. Go, 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 go. 7 years per hour here. Let's make it count.
That's something else. He says 7 years per hour because that's relativity, right? They're further down a gravity well. So time is going, what they're experiencing is much different than what they're experiencing back home. So he's trying to get back home before everybody dies, I guess. See.
Sick of red, itchy mosquito bites?
Sorry about that. I knew they would hit me with a commercial. I thought I had it timed right. All right, skip the ad. Here we go. While we're watching this, quick show a thumbs up if you've seen this movie. I'm surprised Jacob hadn't seen it.
This way.
Oh, okay. Let's keep
About 200 meters.
This is my favorite scene in the movie, by the way.
Gravity's punishing.
Been floating through space too long?
130% Earth gravity. There's nothing here. Should be right here.
If the signal's coming from here. For beacon.
Wreckage.
Recording. And somebody's got to, if I'm saying I'm going to stop recording, somebody's got to keep me honest. I keep forgetting to do that stuff. All right. I've only been doing this for almost a year, but I don't show that many recordings. That's the thing. Okay, so back to this. So, the point I'm trying to make. So, our sun, that's a black hole. Thank you for reminding me of that. Huge gravity well. That makes total sense why you'd have such a tidal wave. Our sun, I don't think our sun could ever produce that kind of a tidal wave, even if we were like Mercury. Mercury's tidally locked now anyway. But okay, so, and the reason is, well, partly our sun's mass, but partly is that inverse square law again. So Neil deGrasse talks about this. I will put this link in the comments. And the only thing I want to talk about was this consequence of tidal friction. Like, okay, so because this brings a lot of physics into it, and I'll just have to kind of read it to you, read along with you here. But it says the ocean tides are not the only effect of these tidal forces. The solid Earth, we have land tides as well, which are on the order of like millimeters, but the land does rise up because it's more interstitially, it's connected. There's more. Like silicon dioxide versus H2O and all that kind of stuff, but it still rises towards the sun, towards the moon. So the Earth, and then Jacob asked last time. He said, "Well, does the air get thinner or is it less dense under that tide?" And I guess his thinking was that the atmosphere itself has tides, and we looked this up a couple of years ago, and it does. We talked about this after. Okay, so we talked about this after our session last time. So I thought it was a good question, though. So anyway, and feel free to ask questions as we're going. You don't need to wait till the end, to come up and ask questions. So the atmosphere itself, we're looking, troposphere and then stratosphere and mesosphere and all those. Those is a thinning out, but it still has mass. And so if it has mass, it's being attracted to the moon. So the atmosphere itself, the atmospheric particles do spread out a little bit more under a tide. Now there's friction involved, so it probably doesn't follow perfectly along with the tide. It probably goes ahead of the tide, but there's also the revolving of the Earth. So there's lots of Earth-Moon systems is really, you could do a whole course in it. It's just complicated physics because you have spinning objects, rotating objects. There's so much, and then there's friction involved. There's so much going on. And then you got the sun, All right, so the daily flexing of the Earth, both solid body and sloshing of the oceans. Now here's the important part. Causes loss of energy to the Earth's rotation. Now it really causes two things. It heats up the Earth a little bit because of friction, because there's friction between all these particles that are being moved up and down and the particles that are rubbing against the shear forces. There's different amounts of, anytime you have that happening, you have heat produced, like, this on a smaller scale maybe, but you have heat produced. Well, so that means that the energy of the Earth rotating, the Earth rotates, it has mostly rotational energy, 1/2 I omega squared, which I is this moment of inertia, and then omega is we know omega, it's how fast the Earth is spinning. I mean, Carson hasn't had that yet, but he'll have omega in the fall. So 1/2 I omega squared is like the equation for the Earth's energy because of its rotation. Well, because some of that energy is eaten up by the friction, because friction's like Pac-Man. I got friction right here. I'm going way ahead for a second. Friction's like Pac-Man here, and friction eats energy. Friction, these little red dots, like in a Pac-Man, is like mechanical energy. No matter where Pac-Man goes, he's eating mechanical energy. If you double back, you don't get it back. So that kind of stuff. Friction is not conserved. It's meaning that you can't, it takes, but it doesn't give back. Like gravitational force, if I'm on a roller coaster, gravitational potential energy, I gain energy when I go up here, but I give that energy back in the terms of kinetic when I come back down to the bottom. But friction is not like that. It just eats and eats and eats. Okay, so going back, hey, it's a variety show. So going back to this, if energy seeping out of the system, I still haven't set up my table yet. I got a little demo on this, but if energy seeping out of the system, then it's got to come from somewhere. Well, it comes from the loss of Earth's rotation. So the bottom line is that the Earth is slowing down. Now, the good news is it's slowing down at about 2 milliseconds a century. So nothing for you to worry about. But the moon is tidally locked with the Earth. So eventually the Earth's going to kind of end up slowing down to will be tidally locked together. Eventually, we're talking, billions. And we're only around for 4.5 more billion anyway, because the sun's going to go a red giant. But okay, so as you might imagine, the Earth has also exerts tidal forces on the moon. In fact, the tidal force of the Earth and the moon are about 20 times larger than the moon on the Earth. So if the moon had an ocean, those tides would be, 30, 40 feet every day, rather than 3 or 4 feet. So even more than that, 60 feet tides, 70 feet tides, if the Earth had water. But so the Earth then, if the moon had water. So the moon then does have land tides, though, which probably is a source. I don't know if it says this here, but that's probably a source of moon's internal heat, is that friction that is caused. Moon's, it is still rotating, but it's locked into us. It can't get out of that rotation rut. It's kind of like a ball at the bottom of a bowl. It can't get out of that rut. Anyway, so it's a more stable situation. Things in physics always tend towards stability. That's why things fall to the ground. That's a more stable situation. Things roll downhill. It's more stable. So potential energy is always trying to lower if it can, if given the chance. Part of the reason for entropy. Anyway, increasing entropy. So enough of that. So the line of distortion is continually being rotated away from this line between the two bodies, causing the bulge, okay, to lead slightly. So the bulge leads, which is weird, but there is then a net torque. Now, torque is a force acting at a distance. It causes things to rotate, which I have in my truck. But when I cleaned out my room. So if I have this stick here and I have this on the end of it, it tends to want to rotate. If I can balance that tends to want to rotate, right? It wants to pull this down. But that right there, that what I feel in my hands is torque. It wants this tendency to rotate. I put a counter torque on it, but so that's what torque. We'll get into torque. We will get into torque, I promise you, before June's over. You have to. You can't do machines. There is then a net torque opposing the direction of rotation, thus slowing down the both bodies. Okay, so it talks about tidally lock. Let's keep going. Why is the moon keeps the same face? Oh, and the last thing about the moon then, so then why is the moon keeps the same face to the Earth? That is why the moon keeps the same face to the Earth. And I'll put this in the comments. But I want to show you an animation. Oh, no, maybe I won't. I got to go back to hold it. I won't have to do much. I can show this. I won't get in trouble for this one. Okay, let me share this real quick. This is an animation, or not an animation. This is pictures taken of the moon each night. Okay, and then strung together. There you go. So you can see that it's the same face because it's tidally locked. It's the same face, sea of tranquility, all that kind of stuff. And then that's why we have the dark side of the moon. Don't look at that too close, man. You're going to get epilepsy. You're going to have a fit. Stop looking at that. All right, let me stop that sharing. It's bugging me. Okay, but anyway, that's taking, over a 29-day period, then just looped. When this occurs, okay, let's keep going now. I think I'm done with all that. Showed that. The last thing I want to talk on that is the tidal heating of Eo. Now, Eo is one of the planets of Jupiter, and it's got this pretty elliptical orbit. And all orbits are elliptical, but eccentricity is how much it differs from a perfect circle. Our moon orbits the Earth in an ellipse. We have a supermoon. We have that time when we have that supermoon, it's closest. It's perihelion, aphelion. And so the Earth, when it rotates the sun, is also an ellipse. But when Eo has a huge elliptical orbit, a large eccentricity. So Eo here, when Eo orbits the Jupiter, it's really being pulled like at its apogee, at its lowest, at its closest point. It's really being pulled. And so there's a huge amount of tidal forces on Eo. And then at the perigee out here, it's still being pulled, but not as much. And so you have all this internal friction in Eo. And I think Eo is like, as I was reading here, I think it's one of the most active, geologically active bodies in the solar system. You have all this magma and volcanoes on Eo. It's just a hellscape because of this, basically because of tides. Anyway, kind of cool, eh? I thought. So I'll put that link in there as well. Okay, believe it or not, we finally made it to Pulleys, and there's more than 5 minutes to go. So before we leave tides, tides is something you're probably not going to learn in physics. I think they may spend a couple of problems on it in college, unless you live by the coast. Anyway, so let's talk about some pulleys and machines. If you have other questions about tides, put them in the comments or in the chat if you want. Okay, so now let's do an introduction here, and then there's a couple of problems I want you to try and work. So you're going to need some paper and pencil. We'll do some real physics here in a minute. Okay, so these are two famous like lithographs that you see, and this is Archimedes. So Archimedes was one that really started understanding pulleys. I think even Babylonians used a form of pulleys, probably simple pulleys, but he was the one to really start to not understand all the physics of it, because no one understood physics really, but some of the geometry involved and some of the mechanical advantage you got out of pulleys. So he would lift large amounts, large objects. Like here he is. This okay. These pulleys, the way he has it rigged up, these are called load-bearing ropes. It's all like it's not all different ropes, but there are different ropes here. But these are load-bearing ropes. This is not a simple pulley system. So I think when I first looked at this, I was thinking simple. But now that I look at it again, I'm going, wait a minute, this is not the case. I'm wrong. I think my value's wrong. I said 800. I think it's more than that now. I got to go back and look at that again, because I was thinking simple pulley system, but this is complex. When you have more than one rope involved, it becomes complex. When it's all a single rope wrapped around, then it's easy to count the number of load-bearing sections. But when there's more than one rope, you have to do it. You have to do this thing with multiplication of tension. So you got tension there, and then this is held in. So that's just all that does is change direction. And then this, if I go this way, if I go tension, then this would be 2T, because there's rules, and we'll get into all that. This is 4T, this is 8T, this is 16T. Okay, so I am wrong. So that's 16T. So with 100 pounds of pull, he could theoretically lift 1,600 pounds. I'd have to look at this again, but that's still considered just a pulley system. It's a complex pulley system. Now we're going to get back into it for the basics. I'm just showing you some big picture stuff. So that's what he would demonstrate, that with one man using pulleys. I mean, talk about a great machine. Talk about the iPhone, 12 of its day was not just a pulley, but complex pulleys where different ropes are used. So Archimedes gets a lot of credit with that. There's stories of him attaching hooks to enemy ships and then pulling them out of the harbor, thus defeating the enemy. Those may be apocryphal. I'm not an Archimedes, and a lot of this stuff's lost, but with the fire at Alexandria and all. But with this system, I think they made this up, and I think the artist got it wrong. It's not a very good system. He gets a mechanical advantage of 3 because there's 3 load-bearing ropes. So if the ox, and plus he has an ox, if he pulls with 300 pounds, you would think he would get 900 pounds out of it. But then they put in a first-class lever in there, and that first-class lever is this one's designed to give a distance advantage, not a force advantage. So you actually cut it in half. So what you could have got 900, you're stuck to about 500 pounds that ox could lift. So it's not a very good system. It has a distance advantage, but I don't know. That doesn't seem like it's giving you a whole lot. You could beef it up by making this complex, or by adding more pulleys, and thus giving your mechanical advantage goes up with each load-bearing rope. So anyway, not a very good drawing. Now, what I said just irritated you, and you don't know what I'm talking about. Now let's go back and let's simplify. So for the next bit of the class, we're going to just do simplified stuff. And so we can actually do some math. Well, first we have the 5 rules of Pulleyland. So remember we said that you have your XY axis, and that's great. And then you can tilt it. You can tilt your XY axis. But in pulley systems, you have your XY axis. This is Cade's announcement. You have your XY axis here. But not only can you take it and tilt it, you can bend it. That's why there's that Salvador Dali watch. Because someone said it once in class. You mean like the watch, the melty watches? Yeah. You can melt the x-axis around pulleys. So the x-axis, so in a pulley system, say we have a pulley system here, and you'll need your pencil, and I don't know if you need a calculator. You can probably just do symbols today. But here's my x-axis, comes up, curls around, and then comes back down. That's all the x-axis. Okay. That means the y-axis, if I do it in blue, kind of comes along for the ride. Y-axis is always perpendicular to the x-axis. And usually you don't care about the y-axis on pulley systems. And then if we have a pulley system like this, say we have 2 pulleys, and we hook that one to the ceiling. I'm just showing you some basics. And then you hook this one to say 100 pounds is standard. Hey, and Nicholas, do you guys do this in AP this year?
We actually, yeah, we work with pulleys a lot because it helps
Good.
with, I think, concepts like angular momentum. I'm not quite sure, but there's also energy as well.
Right.
Rotational energy.
It's a good pulleys are a good lead into, and there is rotational energy involved, 1F, 1Fi omega squared, that kind of stuff. Okay. So anyway, so in this case,
and moment of inertia. Sorry. And moment.
Yeah.
Of
Oh,
inertia.
course. The pulley. Now the pulleys that we deal with are they're Protestant. We say they're Protestant because they're massless. I mean, they're Catholic pulleys in AP physics because the pulley all of a sudden has mass. So old physics joke. So it's Catholic. But pulleys that have mass don't want to rotate, right? When you're pulling on them, they don't want to rotate because they have rotational inertia. Well, in this class this summer, that would be like season 4 of my physics. Maybe season 3 would be we get into massive pulleys. But we just go ahead and say there's like a 5% deduction per pulley, but we keep it simple. Anyway, back to this axis. So now if blue is the x-axis, let's say I start right here. X-axis comes around, wraps around that pulley, and then you pull down with that. So that's all one axis. See what I'm saying? Okay, so the first rule was the rope is a continuous x-axis melted around the pulley. Boom. Rule 2 of Pulleyland is the direction of motion is always positive. So DOM, no matter if this thing is going this way, then here, this is positive. Whichever way the mass is going, that direction of motion the rope is going, that's positive. Okay, because you can't say up is positive, right? Because in this case, it goes up here, then it goes down there. So which one's positive? The direction of motion is positive. That's why I tried when we did free body diagrams to start to get you to just always think that, okay, direction of motion is positive. And that's going to get you through any kind of free body diagram, any kind of pulley system. Where that won't help you is when you're doing conservation of momentum, because in those cases, you have 2 things going in opposite directions. And like in adding vectors, those kind of things, you have to worry about, well, with this way's positive, this way's negative. But for pulleys and free body diagrams, because only one body, direction of motion is always positive. Rule number 3, the tension is the same throughout a tight rope. That's really important. So we give a capital T for tension. So here I would say, okay, this is all, it's this, let me give you a color here. So purple. So this is T, this tension in this rope is T, the tension in this rope is T, the tension in this rope is T. And they're really sections of ropes, okay? More about that later. So that's rule number 3. Rule number 4, the acceleration is positive and the same for both objects. So like one object's going up, one object's going down. What we would have done back in blue equation days is you would have said that the object going up is positive acceleration, the object going down is negative acceleration. Well, that works well for kinematics, but it doesn't work well for machines, okay? So in machines, you say that the direction of acceleration is the direction of acceleration is always positive for the objects. So things that are slowing you down is like friction, moment of inertia, whatever that kind of stuff is. And finally, if you're putting A, B, C on your boxes, box A is always the biggest, box B is the next, box C is the third. Okay, and usually you don't have more than 3 boxes. So here we go. This sheet is APS. It's APS2, Askey Physics Show, sheet number 2. Occasionally I have one little sheet to help us out. So let's do number 1 together. I'm going to let you work on this for a second. I'm going to push pause. And so we're not wasting their time. But what I want you to do on this one is I want you to develop an equation for acceleration of the system, for the whole system. This is all a system. Now, I know it's all a system, but it is, and Carson, you may have some trouble on this because you haven't already done this, but it'll be a good preview for next year. But you kind of take your mental scissors and you cut each one of these out, and then you do a free body diagram on each one. Then you put them together. You have two equations, two unknowns, you put them together. I'll show you something called the Villatorel shortcut here in a little bit. But what I want you to do is do your free body diagram on A and on B. Remember, A is the bigger one. Then go and do your F equals ma, your Newton's second law equations. And my apologies to Carson. And then you add those up. Let's find an equation for acceleration. Okay, I'm going to hit pause and let you try this for a minute, and then we'll come back and I'll talk about it. Okay, so we are back in business here, and I don't know what you did. I know Carson probably just stared at his screen, but the rest of you should have had something down here. But let me show you what I would do. All right, so A is the bigger one. Let's see, I'll make them red. So there is, I always do, I do the bigger one first. I always take care of the big dog because it's going to be the longest vector. So this is tension up on A, but A also, of course, has gravity down. Oh, it's going to, okay, hold on a second. I forgot to say this. The direction of motion, this should be in the rules, but the direction of motion on a pulley is always given in terms of clockwise or counterclockwise. This one's going to go counterclockwise because A is heavier, right? We said that A is a masser, is the bigger mass than B than C. So A is the big dog. So I'm going to make its arrow the biggest arrow in my system. So that is MAG. And for Carson, that's just the effect of the mass of the earth on, which is the weight of A. Another way to say weight is just mg in physics. B, then we said that the tension is the same throughout the rope. So B has a tension up. That is, I'll show the, and remember on systems, like when we did the 3 boxes on top of each other, if there are couples, or not necessarily a couple, but if there are pairs of equivalent or the same length, I'm being careful with my words here, but you got to show the congruent sign. If they're congruent, let's put it that way. In length, you got to show the congruent sign. So the tension's the same because it's a tight rope. B is the weakest, and so it's got the smallest MBG, the smallest weight. Okay, so if that's the case, you guys still with me? If that's, I get into this, and then you all, hey, wait a minute, everybody left. What the? Okay, so so now, first off, any questions? I got to be more like a teacher rather than just a lecturer. I need to be more like a teacher on things like this. When I'm talking tides, I'm waving my hands a lot, but here we're actually working a problem. So let's pause for, I'm not going to pause the recording, but I'm going to pause my voice and stop yapping for a second. Does this, so far, is this okay? Or if not, feel free to ask me a question. Okay. Okay. Everybody says okay, but Carson's saying, what are you doing? Don't worry, Carson. I know it's not okay. All right. So now the next step is, Carson's a preview of next year. The next step is to write the F equals ma equations. And so I'm going to start with the positive because remember direction of motion is positive. So I have MAG minus T equals MAA, right? And this A being the acceleration of the system, okay? And then for body B, I have negative because the direction of motion is positive. So I have negative MBG plus T equals MBA. Okay, so I have 2 equations, and if I'm going to solve for acceleration, I can add these 2 equations up. Notice that it's always good to do that because this guy and this guy are going to cancel. And so Newton would just say, yeah, if you make the whole thing one system, internal forces cancel. The tensions are internal. They kill each other. Just like on those 3 boxes, the normal force between each set of boxes killed each other. That's what happens. So we end up with this equation: MAG minus MBG equals MAA plus MBA. Okay. So ultimately, the equation for acceleration here is A equals the difference of the masses, MA minus MB, over the sum of. I'll pull the G out of that. Yeah. Over the, that'll work, because then I bring that over. Yeah, over the addition of the masses. MA, I haven't taught this in 3 or 4 years. Maybe, man, it's been about 4 years. Okay, so that's my acceleration. And that's kind of a standard. I should put that on the equation sheet probably. I'm working on the next equation sheet. Maybe that should go in there. So it's like the difference of masses divided by the sum of the masses times G. So it makes sense, because if the masses are the same, acceleration is 0, right? MA minus MB is 0. So it makes sense. Both masses are the same. They're not going to move. If mass B was 0, if I plugged in a 0 for mass B, 0, 0, then what does acceleration become for A? Yeah, it becomes G. It becomes G because it's in free fall. A equals G in that case. And that's because mass B doesn't exist. And so it's just A in free fall. Okay, we assume, that's another assumption we make when I teach physics, because we're doing intro-level physics, we assume that the rope has no mass. Now, even AP physics assumes the rope has no mass. It assumes that the pulley has mass, and therefore tends to not want to rotate. But when you want to start bringing ropes into it, and then if it's real machines, you got to bring in the chain, because chains are heavy. And so that whole thing adds a whole nother level, conservation of angular momentum kind of thing. It adds a whole nother level of equations to it. So all we do in here, you go, oh man, look, pulleys are easy. Well, yeah, but we really made the system. We contrived it to be as simple as possible. That's what we do, that's the cool thing about physics. The further you go, the more interesting it gets. The more complicated it gets, the more real it gets. I had Mark Elke, who's now an engineer. He lived down in Florida, and he said once in AP physics, he said, AP physics is cool and it's much more realistic, but it's so much more harder. It's so much more difficult. And that was just one level up. Now, when you take dynamics and statics in college, it'll go another level up. Anyway, don't worry about it. So now let's quickly take this one. We can solve this one in a little bit of time we have left. Using this formula, I want you to solve for what the acceleration is for this system right here. What is it's asking you to do a little kinematics at the end. It says, how long will it take block A to hit the floor? But let's just, right now, we don't care about that. Let's just go ahead and do it. What is the acceleration using this system? Even Carson now can do this. And I know, Carson, it seems frustrating to plug stuff in, but that's okay. Let's get you practiced. That's all. You can practice. And then you'll be, kicking everybody's butt next year. Okay. So so we're going to plug it into this equation. A equals the difference. Well, that's what is it? 9 kilograms is the difference, 15 minus 6, over the sum, which is 21 kilograms, times G. Boom. Which, in other words, A is going to be, in my head, back of the envelope, 0.45. Approximately, it's not 50%. It's about 0.45%, 0.45 G. So it's going to fall. So in other words, block A, which is heavier, is going to fall at about half the rate that it would normally fall if I dropped it. So in slow motion. So that's another reason why we like to use pulleys in class, is because we can put on one side, we can put 1,000 grams, put 1 kilogram. And on the other side, we could put 980 or say that's a bad made up number, 950 grams. Okay. So 1,000 versus 950, the difference is small. And in fact, there might be too much friction. The pulleys I brought home have ball bearings in them. And I'm hoping on Monday night, I can do some demonstrations on pulleys. But anyway, so if one's 1,000 grams and one's 950 grams, then the 1,000 grams will fall to the ground, but maybe at 1/20th the normal speed. So it's kind of like making things go in slow motion. So you can study things in slow motion. How long will it take block A to hit the floor? These guys, 3 or 4, you know this, it's just kinematics, and it's not free fall though. It's orange kinematics. That'll make more sense in the fall, Carson. And then we do another one, a couple more of those. The last one, we got 2 minutes. Okay, there you go. So your homework, if you want to do it over the weekend, if you want to play with one, hey, feel free to play with that one. And I'll show you this kind of work. Okay, I'll show you that's my work, a little nicer version. But if you want to play with that one for Monday, just to see what happens, and another one you can play with on the back, and now we're kicking it up a notch. So we'll probably maybe do one of those on Monday, and that'll be pretty serious stuff. So we're going to get more into serious, hard-nosed mechanics now that I've had my fun with standard model and tides. So that one, play with that one. So it adds a little complication to it. And there's some kind of cool things that happen here, which we'll bring up on Monday, inertia and all. Okay. Well, as usual, that was a variety show. Hope I don't get in trouble with YouTube on the movie, but if you see it, remember, you got to give me 24 hours to get the movie, to get the episode up on the YouTube, you can't, I don't think you can go to YouTube and get it. I think you have to go through the Facebook group because it's unlisted. Maybe I'm wrong. I don't know how unlisted works, but I think it's unlisted on my YouTube channel. It is unlisted, but I don't know. That must mean that I have to send you the link. Well, I'm putting the link on the Facebook group. So anybody, there's like 40 members in the Facebook group, but most of them are alumni or other physics teachers. So I thought, well, maybe if you ask a question and I'm not around, they could answer it. You know, I got different physics teachers on there and former students. Okay. So far I've invited about 90 and 40 or so have seen because a lot of them just don't do Facebook. You know, they're never going to see it. Okay. Jacob's got a question. No. Okay. We're good. Okay. So, it's now 7:30. I promised. Sophia came. When did Sophia come in? Huh. Okay. Maybe she's been there the whole time. I just noticed on my screen. Well, thank you. Sophia, I think, and maybe Jacob too, right now holds the record of coming to the most of these. And I think I will, like I'm putting in Facebook, I'm putting who attended because I think it's, you know, credit to you. In fact, I'm going to take a screenshot of that right now. Don't move. And then I'll list you, if you don't mind, in our private Facebook group, just so I can know. And then I will give you all a certificate at the end, you know, something you can have and show if a college person doesn't believe you. You know, you're trying to say, hey, I did this physics seminar with this crazy man. Here's proof that I did it. But on there, I might say, I don't know, perfect attendance or whatever. I'll try and dress it up. I'm trying to find ways to make it. And Carson, I think, Carson missed one, but he told me why he couldn't make it. Anyway, sometimes you just plain can't make it, you know. But I know a lot of you are watching the recordings. Anyway, so I guess I won't see it on Monday. Have a good weekend. You can try this one. If you want to really challenge yourself, try the incline plane. I bid you adieu. You guys can stick around if you have a question.
Thanks, Mr. Askey.
Thanks, Sophia.
Have a good one, Mr. Askey.
Okay, we'll see you, Nick. I think that was Nick.
See you, Askey.
Hey, Carson. Carson, can I say something? Can I let me turn recording off.